Okay, good afternoon. So my name is Liang, and today, thanks Recon to have give us opportunity to stand here and introduce our exploits of the iOS 11. So as you know, that KeenLab actually participated in the Mobile Pwn2Own 2017, and we got the Master of Pwn title last year. So among them, we actually pwn iOS twice, one for the Wi-Fi, one for the Safari. And today, we will introduce our part of our vulnerabilities in our remote exploit chain. So here is the agenda. We will start with iOS remote exploit chain overview to overview and give you a short introduction of how remote exploit chain of iOS works, and also the sandbox bypass bug and the exploitation, because we think the sandbox bypass bug is a little bit special, and especially for his exploitation method, because originally, at the first glance, we found that the bug is not that good, but after deeper research, we found the bug can be turned into a very perfect bug, which we can achieve 100% reliability of the exploit. And then we will introduce the ROG app installation by only using a userland approach without any kernel bugs involved. So this is also very special because our understanding, the iOS on the iOS platform, the code sign enforcement is very strong, and unlike Android, that you can maybe do something. And in iOS historically, we always use some very advanced technologies to get some code not signed app installed. And then we will demonstrate the remote exploit chain by a demo. And also, because you know, last week, Apple actually released iOS 12, and I will talk about the security hardening that killed our origin chain, remote chain of the last year's Mobile Pwn2Own. And also, because iOS 12 is introduced, then KeenLab is also busy with new research to defeat it. So we will also show something at the end of this talk. So first, we introduce ourselves. So we are both members of Tencent Keen Security Lab, and previously we are known as Keen Team. And my name is Liang, and currently I lead the Pwn2Own team in KeenLab. And personally, I do browser exploiting, iOS and macOS, and the Apple World sandbox bypass research, and also the kernel bug hunting and exploitation. And I'm the winner of Mobile Pwn2Own 2013 iOS category, and also I'm the winner of the Pwn2Own 2014 OS X category.
And hi everyone, I'm Marco. I'm also in KeenLab, and my main focus is hypervisor and baseband. But sometimes I also join Liang with some iOS and macOS research. And I'm also a contributor of a bunch of Pwn2Own in the past 3 years.
Okay, let me continue the introduction. So we are all white hat security researchers, and currently we have around maybe 50 people in our organization, unlike some rumors that we have 2,000 people. That's not true. And among them, 30 of them are the security researchers, and others maybe some marketing guy and developers, etc. And we won several times Pwn2Own winners, and all of us are based in Shanghai. And also we have a blog post here, and if you are interested, you can visit it, and we regularly post some interesting technical articles, and also you can follow our Twitter. And our current focus majorly covers the PC security, the mobile security, and currently some more lower level research, including the basebands and the firmwares. also some virtualization. And as we all know that our car research team is also very strong. We have the Tesla Pwn, and recently we also remotely Pwn BMW. And we also have our APP security research team. And we altogether win Pwn2Own 3 times. In the year 2016, we won both Mobile Pwn2Own and Pwn2Own. And in the year 2017, we won the Mobile Pwn2Own. Okay, so first part, Marco will introduce the iOS remote exploit chain.
So before talking about the exploit, I want to give you some details about Pwn2Own, for who is not very familiar. So last year there was 4 categories, depending on which entry point you choose for your exploit chain. The first one is the traditional one. The entry point is the browser. The user browses a malicious URL and you get exploited. The second one is a little bit more new, and it involves short-distance proximity network, such as Bluetooth, NFC, or Wi-Fi. So your device will interact with a hostile network. And the third and the fourth one involve SMS and MMS and the baseband. So basically, you interact with a malicious SMS or with a malicious base station. And last year, we won 3 of those categories. We won the iOS browser category, iOS Wi-Fi, and the Huawei baseband. So, like I said, there are different type of Pwn2Own targets, and depending on which category you approach, the exploit chain will be a little bit different. I will describe 2. This one is the browser-based one. What does it mean? The user browses a URL, and we get the initial code execution on the application processor. Because a modern device has multiple processors. There is the application processor, which runs your browser and your application. And then there is some Wi-Fi chip or baseband chip that run other real-time system. So it's totally different environment. So in this type of exploit chain, you get code execution in some sandbox environment, such as the browser. And then you need to escape the sandbox by using a different bug and achieve code execution outside the sandbox, where you can leak more sensitive data, such as the user photo or SMS or contacts. Then, if you want, you can chain a code sign bypass if you want to persist your exploit chain, or a kernel privilege escalation if you want to achieve kernel code execution and achieve jailbreak on iOS, basically. The other categories, it's a little bit different. You can see here the entry point is Wi-Fi chip or baseband chip. Initially, with your first bug, you get code execution inside these small processors. And at this point, you have the ability to monitor traffic, monitor SMS, monitor calls. And this is already a very powerful primitive, but you can also chain chip escape bug, let's say, and achieve, for example, kernel code execution on the device and get total compromise, because the sensitive information is contained on the application processor. So you need to escape the baseband, for example. So, as Liang will show you in a few slides, we didn't use any kernel bug to escape the sandbox, and I would like to explain a little bit why. The first and main reason is that the Pwn2Own rules doesn't explicitly require a kernel bug. So we didn't use it because we had already a very powerful sandbox escape in user mode, and it was enough to achieve the goal of our exploit chain because we wanted to steal the photo and install our application. And furthermore, by using a kernel bug, you get only 3 master of point bonus and $20,000 US. And as you might know, the iOS kernel bugs are very valuable, so we didn't feel it was worth it. And the sandbox escape was good enough, so that's the reasons. The last thing I want to share with you about Pwn2Own is the one-click policy, I like to call it. Basically, when you do a Pwn2Own exploit attempt, you have only one click, which means, for example, you browse to a URL and then you cannot touch the device anymore. Or maybe you can join a Wi-Fi network and then your hands cannot touch the device anymore. So this is very important because, as you might know, in the modern device, there are a lot of security pop-up to authorize some action. So your exploit chain have also to bypass those. And it must not require any user interaction or any reboot or any other trick. It simply have to work without user interaction. And I will show you why this is important later. And now I will leave it to Liang for the sandbox bypass.
Okay, so after you got the Safari code execution, I suppose we already got the Safari code execution. The next step is to bypass the sandbox and try to exploit the bug to get the code execution out of the sandbox. So let me first briefly introduce Apple Sandbox. So on iOS, the sandbox rule is actually enforced. You have no way to maybe skip it or something like that. So it is per process based. So each process have a kind of sandbox enforced. So but some critical system daemons like launchd, like AMFID don't have the sandbox because they need to perform some very low-level operation, which sandbox is not that useful for that. And all third-party applications are applied with a container sandbox profile. And Safari also has a separate sandbox called com.apple.webkit.webcontent profile. So all those sandbox profiles are predefined and compiled into the kernel extension called sandbox.kext. And the format is a kind of binary format, and it's not very human readable. So you need to write a tool, usually, or utilize some tool publicly to get the human readable format so that you can understand the profile. So Stefan Iser actually reversed the format very well, and if you are interested, you can refer to his slide. And our strategy on sandbox bypass is quite simple. The first rule is that we are trying to avoid a kernel bug because it's not very worthwhile based on our research. And the second rule is that we should find a system service or daemon with no sandbox applied, the best. But if we failed to find those good candidate, maybe we can switch to some not that restrictive sandbox profile. And we also need that service or daemon can be reached within Safari sandbox. Otherwise, it is not useful. And also, the last but not least rule is that the more complex the interface is, and of course, we like this kind of attack surface better because it might introduce more bugs based on our experience. So we write an internal tool which can review each process and see if there is some sandbox profile enforced. So here we can see that a process named backboard D is very interesting. It has no sandbox profile. Here you can see the SB profile field is 0, means no sandbox applied. So why we choose this backboard D? Because first, as I just mentioned, there is no sandbox, and it contains many complex interface. And I use Jonathan Levin's tool, JTool, to dump some interface. And you can see that there are a lot of. And the third reason is that it is actually the iOS version of Windows Server, which handles some Windows-related stuff in the user mode, and this service is a bridge between the user mode Windows-related stuff to the kernel graphics driver. So this service is like a bridge between two components. And also we have previous research on Windows Server service a lot. So if you are interested, we 2 years ago, we have a talk on Black Hat conference, and you can refer to it. So based on that, we decide, there is another thing is that Backbody actually not only the Windows Server, but also it handles some, on iOS, there is a special operation called touch. And in the macOS, you cannot touch. So the touch involved some IOHID interfaces, which are special on the iOS. So it also resides in the Backbody process. So that's also interesting attack surface. So based on the check of the sandbox profile, we find that at least 3 interfaces can be reachable, 3 sets of interfaces. One is the CA render server. The second one is backbody.hid.service. The third one is the IOHID event system. So before we actually talk about our bug, I'd like to mention Yanbia's bug because it is caused by similar problem, and luckily it is not a bug collision in the Mobile Pwn2Own 2017, but in the disclosure room, actually the Apple engineer mentioned that we have a very similar bug with the Yanbia, and make me very nervous at that time, because if it is a bug collision, our Pwn will be failed. But actually it's not, because his bug is in kernel, and our bug is in the userland. And at that time, he also just submits the bug. So our bug is not based on the study of him. So it's just a coincidence. So his bug is caused by the IO surface developer not fully understand the upper layer of XNU implementation. So I will say about it. So there is an interface which you can reach from the userland, and this interface will accept a user-provided port, and it will check if it is already exists in IO surface notification list, and if it finds it exists, it will try to release the port and return an error code. But in the XNU implementation, it is like if so there is some rules based between the actual driver implementation and the system implementation, which is if the routine handler returns the error, the XNU is actually responsible to free the message. But if the routine handler returns success, then the actual driver actually takes the ownership of that port, so that the XNU should not free that port. So from the code, you can clearly see this logic. But actually, the IO surface implementation is not aware of that. So we learned a lesson from it. But at that time, we haven't learned it. We just found out by ourselves. So the problem is that the handler incorrectly frees the port, and the XNU frees it again because it returns an error code, and it caused the double free. So is there any similar problem also exists in user mode? Because MIG is not only kernel, but also a large part of them resides in the user mode. The answer is yes. That is our bug in Mobile Pwn2Own 2017. And it's in IOHID event system interface set. And it's actually an interface called IOHID event system open. And this interface actually took 2 OOL descriptor contain your serialized data, and the function will try to deserialize it. And the implementation of this deserialize is buggy because it first try to unserialize it, and then it will free the OOL memory because he thinks that the CF object has already been created, and the OOL memory for the serialized data is not needed. So this is also not a big problem, but here the following function is buggy because it then tries to call a function called IOHID event system connection creation. And sometimes this function will return failure. And it also calls the whole routine handler return failure. But at that time, the OOL memory has already been freed. So after the routine handler is called, you can clearly see it checks the return code. And if the return code does not equal to success, which is 0, then it will try to call mark message destroy again. Not again, once. And that function will actually free that OOL memory, which already freed by the unserialized function. So that's the problem of the double free. So the next thing for us is, of course, try to exploit. But we need to ask ourselves, it is exploitable because of some reason. First, it is OOL memory double free, which is freed by the function vmdallocate. And the second thing is that it is freed on the same thread within a single interface. For example, if you can make a double free in 2 interfaces, like you call it, and you wait unlimited time, and you can free it again, then this kind of bug is perfect. But definitely it is not the case for our bug. So the question is it exploitable? So let's see in a general case how to exploit a double free bug. It's like between the 2 free, you actually need to fill in the freed memory in between. And then you can make that object be freed. Yeah. So the best case is that the 2 free memory primitive involves some vtable call, so that after the memory A is freed, you insert object B where every byte of that object can be controlled. And then you free it again. And the second free involves some vtable operation. So its vtable already be changed to your controlled value so that you can get the code execution. But here, definitely, it's not the case because the 2 free primitive is not, does not involve any vtable call. It's actually the vmdallocate, which is implemented by POC. So it's not possible here. So the second sort for us is like we can use actually a double free to trigger another double free. So in this case, we make it more complex. Like we can try to free the memory A, and then we fill in a vtable involved object into that memory, and then trigger the memory free again, trigger the bug double free. And then we can fill in a content controlled object, which I name it object C. And then we free object B, because that object we insert is vtable involved, and we can, of course, free it for once, but because of that bug, we free it twice. And in the second free, I think its vtable has already been changed for our user-controlled buffer so that we get code execution. So we have to, before a successful exploitation, we have to resolve several stuff. The first thing is we need to fill in object B, which is quite important. So the difficulty is that the double free is in the same thread. We cannot inject our code in between. That's very bad news. We also need to, because to the nature of this bug, we have to make the IOHID event system connection create function return failure, in which is the only function we can allocate some objects, which we call object B. But the good news is that the IOHID system open accept actually two messages. Both of them can be serialized data. So it is possible that we free the message A, the OOL1. And in the OOL2, we actually make some objects doing the unserialized and fill into the OOL1 memory. That's very possible, but it is still not able to do a successful exploit because that needs our memory to be freed first by triggering the double free, and then we can fill in another object. But because of that, the consequence is not correct. It tries to free the unserialized object first, and then trigger the second double free. So the sequence here is not the same order with what I want. So we also give up this strategy. And is there any options available? Of course. Because as I mentioned that there are at least 3 services which are reachable from the Safari sandbox. So we can leverage another service called the CA renderer server, and it is in another thread. So it's a perfect candidate. So we can just do a race and make our object fill in between two allocations in another thread. So after deeper research, we found that in the CA render server interface, there is one interface called X register client options, which takes 4 port and OOL message, and that OOL message can be unserialized to a CF dictionary, and its content can be controlled by the user. So it's that CF dictionary can also be persistent in memory until we call a function called xDelect client. So it's a very perfect candidate to fill in. To be as object B to fill in that memory. So, but the problem is there any other, is any method for us to make a stable race? Because here, if we do this kind of race, the time window between 2 free is small, and we cannot ensure that we can 100% fill in it. And if it failed, it makes the exploit very unstable, maybe crash. And you can see that backboard D cannot crash, otherwise it is like a respring, and the screen will freeze, and it will just behave the same as a phone restart. So in a usual case, we just do like brute force allocate on one thread, and another thread try to trigger the bug again and again, but it's not stable. And again, the good news is that the IOHID event system open, that function accepts 2 OOL messages. So it is possible that you free the message 1 first, and then in the message 2, you construct a very complex serialized data, and you make the unserialized operation very slow. And so that thread can be penned in between 2 frees. That's very perfect. So here we show a code piece of our exploit that we make a CF dictionary containing a CF array of many elements, and each element equals to a string, a very short string, which is served as a tagged pointer to save some money, so save some memory. Sorry for that. Save the memory, and by the experiment, it takes around 8 to 10 seconds to finish the unserialized operation, so that that thread is like hanging at that unserialization function, which is perfect. So we have enough time for that the second thread to fill in the data. But another challenge for us is that we are trying to fill in a CF object, but the field memory is allocated by VM allocate. So CF object belongs to the heap, and that VM allocate is allocating virtual memory. So it's not basically it's not a very ideal idea. But luckily, on the iOS system, we found that if you use the CF allocator allocate to allocate a CF object, and the size is more, if the size is more than 20,000, then it will directly use the virtual memory, which means you can construct a very big CF object. And is there any such object that its size can be controlled? Because usually a CF object has some headers and maybe a pointer, and the pointer points to some memory. But after our check, we found the CF array doing unserialized is the best solution, because it contains some metadata in the header, and its elements are all inlined just after its metadata, so you can fully control the size. And also, we need an Object-C, which can fill in the freed CF object. And that object, you need every byte to be controlled. And also, we found a candidate which is CF data. So if the CF data is very large, then its header and its pointer, its real memory, it will be separate, so that you can make a CF data's pointer, and with every byte, user can control. So let's involve this exploitation strategy a little bit complex. So in the left part, we just freeze OL1, which is in size 40,000. And in between, we make a very complex message to hand that thread. And in another thread, CA render server, we call the X register client options. First time, we try to allocate 0x40,000 sized CF array, so that we can make sure to fill in the freed memory. And the second time, and then the second free is triggered, so that the CF array is freed. And then in the middle of that, we can see we try to call X register client options again. This time, we try to fill CF data's pointer, where every byte we can control, and its size is 40,000 also. And after that, we trigger X delete client to make some virtual table call on the freed CF array, where its vtable has been controlled by our data, so that we can achieve code execution. So this is our planned strategy, but in fact, it doesn't work. Because instead of the CF array filling into the memory A, we found it never be able to fill in the memory A. We have to find out the root cause. So after check the source code of the core foundation code. Actually, it's not open sourced now, but in the early version of macOS, it is open sourced. So I checked the early version, maybe 10.9. Yeah, 10.9, it is open sourced. And you can find the unserialized operation involved a function called CF binary plist create object filtered. And before it creates the CF array, it actually creates a temporary variable which stores every element pointer. And in another function, CF create transfer, it actually creates the real CF array. And it sets the header, the metadata of that array, and just copy the content of list after the metadata. So the problem is that it is not the CF array fill into that memory. It's the list variable fill into it. So it make our exploit failed. So, but the good news is that we can find that the allocated list it is different in size with CF array, because CF array includes the header, the metadata, but the list not. So the list size is smaller than the size of CF array. So we have a better solution. So we can change memory A to another size with a bigger size, which is 44,000, 0x 44,000. And in the meanwhile, we can pre-allocate many hosts with size 0x 40,000. So we can make sure that list object always filled into those 0x 40,000 hosts, while the CF array will be successfully filled into memory A. So we adjust the exploit strategy and make the final version. And because we pre-allocated a lot of free hosts, so that the list object always fill into the 0x 40,000 free hosts, so that we make sure that our CF data successfully fill into memory A. So after that, we make the code execution, but we still need to consider some problem. First, how we get ASLR bypassed. And on iOS, it is not a big problem because we launched the exploit from Safari. And on iOS, every process shares the same DYLD shared cache, which stores the library. And because we defeat Safari before, so we can use the same offset, same base value to be used in backboard D, and the backboard D ASLR is also bypassed. And also we get code execution because CF array is a kind of vtable-like structure. Although it's not a real vtable, it's called some Objective-C structure. And after you control that first 8 bytes, you also can get PC controls. And there is a FRAC magazine article showing this. And if you are interested, you can refer to it. And finally, we can see we triggered a crash, and we can have one register controlled to 1990, which means that by proper ROP, we can get code execution very stably. So the next part will cover the ROG APP installation, and Marco will introduce it.
So after we got code execution outside the sandbox, now finally we can steal the photo and install our application. And I will show you how to do it. But first, I need to explain you what's the obstacle on iOS. Like I said before, on iOS there is the code sign, and it's enforced basically on everything which is traditional executable code. There are some exceptions, sorry, but like GIT code, but we will not cover those because it's not the regular executable case. So on iOS, basically all the code must be signed by Apple or by a developer or enterprise account. Those last two options are more appealing because we don't have the Apple private key, unfortunately. And So these two options are more interesting, but they require user interaction. You can see here on the right, if you install application with if you sideload an application, you have to click trust to trust this developer. Yeah. But like I said at the beginning, we cannot perform any kind of click because the context doesn't allow us. So this wouldn't work. And if you take like 30 seconds to compare iOS to Android, it's very interesting because on Android you can just drop an APK and you can self-sign your own code basically and it just run. But instead on iOS you cannot. On newer version of Android is a little bit better because you have to authorize manually with some pop-up, some sensitive action, but your code is still running. The malicious code is already running. So to summarize, on iOS it seems much more difficult. So how this was done in the past? iOS persistence in the past traditionally involved a much more complex approach, like a kernel exploit and untethered binary, which use some complex native code sign bypass, like with overlapping segments and stuff like that. But like we said, we don't want to burn any kernel bug, and so we needed to find another solution. The second obstacle on iOS when you install a new application is that you have to authorize the use of the network. But we needed the network because we needed to steal the photo. We need to send them to our laptop. So we definitely needed the network, and we definitely cannot click on the pop-up. So we needed to bypass also this additional click. So what about if we try to do the traditional way, if we try to install an executable? So we needed somehow to bypass the code sign. We might be able to do it with a developer certificate and a lot of reversing. We need to automate the trust click, again, a lot of reversing, and the network connectivity, again, a lot of reversing. But we don't have so much time, to be honest, and we want to find some easier way. Luckily, on iOS, there is a nice feature which allows us to bypass the code sign very easily. It's called web clips, and basically, iOS offers you the possibility to install native application, but they run HTML inside. So there is no real executable code. And luckily, we have a very good sandbox escape, so we can install one of these HTML-based applications from our sandbox bypass. And inside this native application, we will bundle our WebKit exploit and our sandbox bypass. So in this way, basically, when you click on the application, it will run the exploit chain again, and you will get a native code execution outside of the sandbox every time you click. So luckily, Apple cannot remove this feature, so thanks. And so we just installed this thing, and our exploit chain is very reliable, like Liang said. So every time you open it, it simply re-exploited the device, and it just works. Actually, this topic was covered a little bit also in the past, especially in previous jailbreak, but it's not very documented even online. And nobody, I don't know why, but nobody used it at the Pwn2Own contest. But it's actually very good for the rules of the contest because it saves you a lot of time and a lot of bugs. The approach is actually similar. I don't know if you remember, like 2 years ago, there was the advanced persistent threat called Pegasus. They used a similar idea to bypass the code sign and make their jailbreak untethered. So the idea is, if you want to bypass the code sign, you cannot, of course, use real code. You have to use data to launch some other kind of exploit. So they placed a JavaScript file in the file system, and then they moved or symlink JavaScript code command line interpreter to run this JavaScript file every boot. And this JavaScript file contains an exploit, so they gain native code execution and they jailbreak the device again. So their malware implant can run at every reboot. So basically, we do the same, but instead of using a JavaScript file, we use a HTML exploit with a DOM bug, and we bundle it inside the web application. So now I will go through to explain to you basically the process to do it after quite some reversing. So to start this, we will assume that you are already out of the sandbox, because that part was already covered by Liang. And the minimum requirement to do this is to have the mobile user without a sandbox or a very good sandbox profile. So you have to drop some files inside of this folder, library web clips. You need to make this folder, and you just have to bundle info plist like every traditional application. Then if you want, you can put your exploit and the icon. In the info plist, there are some undocumented flags, but they are very important. Of course, a URL, which you can specify like a URL on your laptop or on your server, which will serve your exploit. You can see here we specify like exploit.html. The second undocumented flag is more important, actually, is full screen flag. Because if you don't specify it, or if you set it to false, when you click the application, it will actually open Safari. It will not run a native application. So this full screen flag is truly essential, because if you specify it, your exploit will run inside the web.app instead of mobile Safari. And as an advantage, you get that the sandbox is better. So, like I said, our exploit.html will just contain one WebKit bug to get the code execution, then the sandbox bypass as covered by Liang. And again, we can steal the photo and gain code execution. So, but not so simple. If you just drop the file, actually your application will not show. The screen will be empty. You will not see the icon. So we will not succeed. So after reversing some IPC, we finally found a way to refresh the application list and show our application on the screen without rebooting the device. So finally, we have that icon on our screen, and we can show the ZDI guys that we successfully install our application. So let's review our roadblocks and see what we bypassed. So like I said, the first roadblock was code sign that you needed to approve. This is not required for web clips because they have data only, so we bypassed it. The second one is Wi-Fi and the connectivity. This one is also bypassed because it's a web application, so they need a network by default. So finally, we achieved the rogue application install without any click, without using a kernel bug or code sign bypass. So I think the lesson learned is that if you are doing this kind of competition and games, you sometimes need to study carefully the rules and find some way around, and it can save you a lot of time and bugs. So now we will do a demo. We will show actually the Wi-Fi compromise. The phone will connect to our Wi-Fi. We will get initial code execution inside a web view with a WebKit bug. Bypass the sandbox, steal the photo, install the application, and then we will reboot to show you that the application is still there. Oh, okay. Okay. So now we will show to you the iOS version, which is 11.1, which it was the latest one at the time of the competition. And here we are showing you that our application is not installed. This is the photo that we will steal, which is our ugly penguin in our office. Now we will connect to our Wi-Fi, which is unsurprisingly Marco 123. now a browser will pop up, which is an iOS feature, which we will exploit, and then launch the sandbox bypass. And you can see now that I speed up the video a little bit, but you can see that our application is installed. And now we will reboot to show you that the application is still there and it will run. Let me skip a little bit. Yeah, the application is there, and now we will click, and I will show you my laptop where the photo will be sent to show you that we really stole the photo. And that's my laptop with the photo. Thank you. And then now I will give the microphone to Liang for iOS 12.
Okay, so everyone knows that last week Apple actually held a conference, WWDC, and after the WWDC, they released the first beta of iOS 12. And one of the major sandbox hardening is that they introduced a sandbox profile called backboard D, which means backboard D is no longer you can do anything. Yeah. So it limited some unnecessary file creation and data write ability. And you can see that it limited your ability to write only to these kind of folders, which means you are no longer be able to write into web clips folder, so that it killed our previous exploit chain if we target on the backboard D. And also, iOS introduced some new features like some hardened AMFI and etc. And we spent around 2 weeks, maybe less than 2 weeks research. And currently, we make a video of showing the latest version of jailbreak.
Wait. Click.
Double click.
Yeah. Okay. I'm full screen.
Okay. So you can see that this is the iPhone 10, and it installs the first beta of iOS 12, which is the latest version, beta version at today. Yeah, you can see no new update. And you can see the version is iOS 12. And we install an app, which is pre-installed app, and it's our internal tool, and we click jailbreak, and we first get out of the sandbox, and then exploit a kernel bug. And after the kernel exploit is successful, there are a lot of things you need to do, like the AMFI, like also on the iPhone 10, there is AMCC. And then another mitigation is remount RW. And after that, everything works fine, and it did a respring to make some service restart again. Yeah, you can see this video is shot in the morning of 2 a.m. So, yeah, I work nearly failed for that. And you can see we install Cydia, and then we can see the Cydia showing the latest version of iOS 12, and it's jailbreaked. Okay.
Play from current. Yeah.
Okay, lastly, I would like to thank the following people. Some of them are our colleagues, and Window is from Pangu team, and also we read Jonathan Levin, and his amazing book is very useful for our research. And that's the end of our talk. Any questions about that? Okay, if no questions, thank you.
Thank you.
Thank you.